We have seen equations where the unknown object was a real number. Then we have seen equations where the unknown object was an unknown vector. Now we are going to talk about equations where the unknown object is a matrix. Sometimes this is called matrix equation, but this term is sometimes used even for equations where matrices appear, but the unknown object is a vector. So today we mean a real matrix equation in the sense that the unknown object is a matrix. If we have a simple equation like A plus X is B, then X can be written as B minus A, and if A and B are matrices, then we just subtract two matrices, no problem, in the sense that Xij is Bij minus Aij. But when multiplication comes into play, we must pay attention that if we multiply two matrices, then in most cases the order is important. Multiplication of matrices is not commutative. So this is the only thing we must pay attention. So consider the following equation. X times A plus 3x is equal to B. And A and B are two given fixed matrices, namely A is 1, 1, 1, 1, and B is a matrix 2, 1, 0, 0. And we want to find a matrix X such that this is true in the sense for all entries in the two matrices on the left and on the right. What will be the shape, what will be the dimension, the size of the unknown matrix X? If we have a 2 by 2 matrix on the right, we should have a 2 by 2 matrix on the left. And 3 times a matrix has the size, the dimensions of X, so X must be 2 times 2. If it were just numbers, we could factor out X. And no matter whether we factor out to the left or to the right. For matrices, we can also factor out X, but perhaps before, when we factor out X, we want to remain here not a number, but rather a matrix. So first we rewrite this as 3xe. E is the identity matrix, and for a 2 by 2 case it is 1, 0, 0, 1. Now we can factor out X to the left, and we have X times A plus 3e is equal to B. Now if it were just numbers, then we would divide by this bracket. This is a matrix, and we don't say we divide by a matrix, we rather multiply by the inverse. So, first we should test whether the inverse exists at all. So let's write down this bracket. A plus 3e will be a matrix. A is 1, 1, 1, 1. And 3e is, if e is 1, 0, 0, 1, then when we multiply by 3, we have 3, 0, 0, 3. We can add these two matrices, and we get 4, 1, 1, 4. Now, to test whether the inverse exists, we compute the determinant. And this is 4 by 4, 16, minus 1, 15. Well, and what is important is that this is different from 0. That means the inverse exists. A plus 3e inverse exists. That's good. How to find the inverse? For a 2 by 2 matrices, there is a quick trick how to find the inverse. Namely, if you have a matrix A, B, C, D, then the inverse can be found by swapping the elements on the principal diagonal and multiplying these two elements by -1 and dividing by the determinant. To to verify that this is indeed up to the scalar coefficient, the determinant, that this is inverse to this, we can multiply these two and we should get the identity matrix. So we have AD minus BC minus AD plus AB, CD minus CD, and minus BC plus AD, that's what I did, AD minus BC. That means if we have a matrix 2 by 2 with elements A, B, C, D, then the inverse is this matrix divided by the determinant, AD minus BC. Because if you divide it by AD minus BC, we have the identity matrix. So we can use this trick to find the inverse for the matrix A plus 3E. A plus 3E inverse will be 1 over the determinant, which is 15, so 1 over 15, times the matrix that we find from this by changing the row of A and D. But if we swap 4 and 4, this is the same, and by multiplying the other two elements by -1. So instead of 1 we have -1, and instead of 1 we have -1. It's a good idea to multiply these two matrices to be sure that the product is the identity matrix. That means this is indeed the inverse. So we can go back here, and when we multiply from the right of the inverse by the inverse, A plus 3B inverse, then it removes this bracket and we have x alone on the left, and on the right we have the solution. B times A minus 3B inverse, A plus 3B inverse. Yeah, let me check this with my preparation. Yeah. Well, so we can use the numerical values. B is 2, 1, 0, 0. And A plus 3D inverse is here, 1 over 15 times the matrix 4, -1, -1, 4, which is 1 over 15. And the product of these two matrices is 8 minus 1, which is 7, minus 2 plus 4, which is 2, 0, 0. And this is the result of the matrix X that satisfies this equation. If you like, you can multiply this coefficient, you can multiply by this coefficient each entry, so that you have 7 over 15 and 2 over 15. We can verify this by considering the left-hand side and the right-hand side of the equation. So on the left, we have x plus a, x times a, plus 3x. Okay, let's evaluate the left-hand side to verify the solution. X is this matrix, 1/15, times 7200, times A, which is 1, plus 3x, that means plus 3/15. We could reduce this fraction, but I will leave 15 because we have also 15 and we will add these these values. 3x and x is 7200. So we have 1/15, and here we have 7 plus 2, which is 9, 7 plus 2, which is 9, 0, 0. Yeah, we could reduce this fraction as well. Okay. Plus, and now I will write 1/15, and I multiply by 3 to get 21,600. And now we can add these two matrices, and we have 30, 15, 0, 0. And now when we divide by 15, we have 2, 1, 0, 0. And so that's the matrix on the left. And on the right we have B, which is B1, 2, 1, 0, 0, which is this matrix. So this was the equation with these values, and we can solve the equation using the inverse, but before we should test whether the inverse exists at all. Here we have the solution, and we can verify the solution by direct substitution into the left-hand side and the right-hand side. Note that if we change this equation by swapping x and a, instead of x times a, if we have a times x, then for numbers, that makes no difference. But for matrices, it does. A and B are the same. And here we have XA, we have AX plus 3EX. And now we must factor out x not to the left, but rather to the right. And we have A plus 3E times x is B. And A plus 3E, not BE, 3E. And we have the same matrix as before, so we compute the determinant. First we compute the matrix, we compute the determinant, we find the inverse, and then we multiply by the inverse, but now not from the right, but rather from the left. A plus 3E inverse. We multiply by this from the left, because this is on the left. And then we arrive at the result that x is B multiplied by A plus 3E inverse from the left. That means A plus 3E inverse times B. But this will give a different result than in the previous case. We have A plus 3E inverse already here, which is 1/15 times 4 minus 1 minus 1, 4 times B, which is 2, 1, 0, 0. So the result is 1 over 15. And now we have 8 minus 1, which is 7. 0 minus 1. And minus 2 plus 4, which is 2. And finally 0 plus 4. So you see this seemingly small change changes the result completely. We have a different solution for this different equation. And we could verify this by comparing the left-hand side and right-hand side of the yellow equation. In some cases, it is not possible to come to the solution in this form. Namely, if we multiply the unknown matrix X both from the left and from the right in different terms. If we have, say, AX plus XB is C, then too bad, we cannot factor out X. We must solve this just comparing the individual entries, individual components of the matrices.